Rietveld refinement of Naproxen racemic mixture using GSAS2. Part 3. Refinement steps detailed explanation. The mathematical goal of the Rietveld refinement is to minimize the difference between the intensity of each point in the observed diffractogram and the intensity of each point in the calculated diffractogram. So do the difference between them and square and multiply by a certain wave factor, and do this summation throughout all the points present in the diffractogram. So the goal is to minimize as much as possible this summation, which in other words means like to minimize the difference between the calculated and the observed intensity. Okay? The intensity of each point that is calculated by the refinement depends on the many factors. In general, those factors are structural and instrumental parameters. Okay? So here on the screen we have an equation that tells how we can calculate intensity for each one of the points. So there are many parameters that you can see on this equation. For instance, this S phase means the scale factor, okay? Then the modulus of F8KL for phase 2 squared, so that is the integrated peak intensity. Then you have peak profile, which is related with the peak shape, okay? Then you have the peak position shown here as well. And then we have a component from the background. So what happens is that, as you can see, there are two summations contained on this equation. This most internal summation, it relates with all the points for a certain phase, okay, in the diffractogram. Whereas this most external summation, it refers to each phase. So suppose you have a multi-phase diffraction pattern, okay? So you have to do this summation for every phase, okay? This internal summation, and then multiply that by the scale factor, and after that do a final summation for all the phases present in the X-ray diffraction pattern. As we saw, there are many different parameters that can be refined in order to obtain the calculated X-ray diffractogram. Obviously, we are not going to refine all of them, but we're going to refine some of them, okay? The ones that are going to refine on this demonstration are the scale factor, the background, the unit cell parameters, the profile parameter functions UVW and XYZ, sample transparency, and sample displacement. For each one of them, we're going to see some details about the equations that are related with each one of those factors, and then we're going to demonstrate where on GSAS you can check the box related with that particular factor, refine that, and how refining that particular parameter can affect the calculated X-ray diffractogram. Scale factor. The scale factor is a parameter that takes into account a set of instrumental parameters all gathered together in a set, okay, that you generally call INST in this equation. Then we have a few parameters that are related with a particular crystalline phase, which are the volume of the unit cell of the phase of that particular material, the density of that particular material, and the wave fraction of that particular material. And then we have a feature that's particular from the sample, which is called the mass absorption coefficient, which we're going to see with more detail later, okay? So basically, by doing this product shown here, so the set of instrumental parameters, multiply by 1 over the square of the volume of the units of that particular phase, multiplied by the ratio of the wave fraction of the phase over the product between the density of the phase and the mass absorption coefficient, we get the scale factor for that particular phase, okay? So basically, when you are refining the scale factor, what you are doing is you are changing the set of those instrumental parameters, and then you may be changing like the density and the volume and the wave fraction of the unit cell of that certain phase. Remember that the density and volume, they are all dependent on the unit cell parameters, okay? So if you change later the unit cell parameters, we may change the scale factor as well. We finished the previous video by setting up the limits to the X-ray diffractogram. So we set the limits start at 2 theta equals to 8 and finish that in 2 theta equals to 120. Now we're going to start refining the parameters in this refinement. The first parameter we are going to refine is the scale factor, okay? So to refine the scale factor, we go on the left side panel, we click under the PWDR option, we click the sample parameters, okay? And then we see that's checked histogram scale factor, okay? The scale factor is going to stay checked throughout all the refinement. So we see that's checked, so you can come here, calculate, and then refine. And then that's going to ask us to save the data, okay? So let's choose the folder to save it. Once we saved, it's going to start to refine the scale factor. So you see that now that refinement started, we have like a calculated pattern which shown in dark green and a background which shown in red, okay? So that's the visual clue, the visual feedback we have from refining this parameter. But you can have a quantity. So first, that's going to ask us to load the results. So we accept the result, we click OK. And then we can have some idea about the quality of the refinement. So you go here, covariance. And then we see that the RW is around 50 and the goodness of fit is around 12. Okay? So we're going to follow these two quantitative parameters throughout the video to see if by refining each parameter they're going to be able to be improved or not. The background. The background can be calculated according to this equation over here, okay? Where there's the summation between the product between the coefficients b and the coefficients t prime. The summation is done throughout all the points throughout the X-ray diffractogram. So the factor T prime is shown here. So it's again a summation where it takes into account the 2 theta position for each point, the minimum 2 theta position and the maximum 2 theta position. Okay, so then this multiplied by a certain coefficient Ci. So this summation is done throughout all the points in the diffractogram, okay? And then they're taken into account here. And what is refined in the refinement are the coefficients Bi shown here, the B coefficient shown here, okay? So in other words, the number of terms that will be present in this summation over here, that will be dependent on how many terms we choose to be present during the refinement in the Chebyshev polynomial function, okay? So if we use order 3 polynomials, then those 3 term, we're going to get 3 terms, 3 B terms. If you choose a 5-term polynomial, you're going to get 5 B terms from the refinement, okay? So in summary, what is refined and is obtained throughout the refinement is this B coefficient, okay? According to how many terms the Chebyshev polynomial function has. The next parameter we are going to refine is the background. For doing that, we go to the left side panel, and then under the option the PWDR, we click in the background, which is the third option. Okay. Here on the background, we are going to check the option refine, and then you're going to use the function Chebyshev minus 1, and then you're gonna keep the number of coefficients equal to 3, okay? So that's set as it is. So you click also the background, that's going to stay checked throughout all the refinement. So you come here, calculate, and then refine. So the refinement is going to start. Then we'll accept the new result. And then let's click in the covariance to look at the RW and goodness of fit values. Okay, so yeah, so basically there's no like a big improvement regarding the RW or goodness of fit yet. So basically they're around the same values. RW around 50.33, goodness of fit around 12.03. Okay, so let's refine the next one, the unit cell parameters. So the unit cell parameters, they can be calculated according to this equation, which is derived from the Bragg's law, okay? So basically, the 2 theta position of a peak with a certain set of Miller indices is equal to 2 times the arcsine of lambda over 2 times 1 over the D spacing, plus delta 2 theta correction, okay? The D spacing, some of you might already be familiar with the equations, and you may know that it depends from the crystalline system of the material, okay? So as example, we're bringing here the equation that correlates the D spacing, or the square of the D spacing, with the set of Miller indices and set of the lattice parameters, specifically for orthorhombic structure, okay? Orthorhombic crystalline system. For less symmetric unit cells belonging to less symmetric crystalline systems, like triclinic, so the equation becomes more complicated. Whereas for equations with, like, for unit cell belonging to more symmetric crystalline systems like cubic, the equation is simpler, okay? What is important about understanding about this equation is about the corrections that relate with the 2 theta. So that correction, it gathers many different parameters encompassed on that, okay? Can be like the eggshell divergency of the beam and the absorption of the sample. So all of them, they accounts for these possible corrections. Another thing about the unit cell parameters is it's very linked to the 2 theta, okay? And with this spacing. So that's one of the most things to be refined in order to set the correct peak position for the calculated diffractogram, okay? So if you are willing to adjust the peak position, so the position where the peaks show up in the calculated diffractogram, probably the unit cell parameters is one of the first factors that you'll go for. Now we are going to refine the lattice parameters, or as the SAS call, unit cell parameters. So on the left side panel, under the menu phases, we click in the name of the phase that you gave, so Naproxen racemic mixture in this case. And then they're going to open like a couple of tabs. We keep the first tab, that's general, and then we check the box refine unit cell, okay? So you see that we have placed here values for A, B, C, and volume in a certain space group that all came from the CIF file imported. Now those values, they will be refined. So you click refine here, and then you click calculate and refine. So the refinement is going to start. we see that apparently the RW is going down, it's a good signal. So we accept the new result by clicking OK. And then you can check the parameters in covariance again. Now the RW, which was around 50.33, it went down to 49.34, so it was improvement. Same happened for the goodness of fit, which was around 12 something, now it's around 11.82. So definitely there was improvement by refining the unit cell parameters. The peak profile. So the peak profile, it models functions to the peak shape, to the observed peak shape. So it models a function to that, to describe that. GSS2 uses a function called pseudo void, okay, in the refinement and to model the XRD peak profile. Particularly the pseudo void function, it's a convolution of the Gaussian function and Lorentzian function. That's what is trying to be shown here on this diffractogram on the screen. So basically, the Gaussian function is the red one, Lorentzian is the blue one, and the convolution of both of them, they give the pseudo-void function. It's the function used to describe the peak profiles by the GSS2. One important parameter correlated with the peak profile is the full width of half maximum of the peak, the FWADM of the peak. So for pseudo-void function, the FWHM depends from the FWHM from the Gaussian component, which depends from parameters U, V, W, and Z, and the FWHM from the Lorentzian component, which depends from the parameters X and Y. Okay, so throughout this refinement, we'll be trying to refine all those parameters, all these 6 parameters, U, V, W, X, Y, and Z. Okay, so all of them will be possible to be refined, and are going to refine them progressively and see how it impacts the peak profile for all the peaks, and how it impacts the quality of the fit of the calculated diffractogram to the experimental diffractogram. Next, we are going to refine the profile parameters. For doing that, on the left side panel, under the menu PWDR, we click Instrument Parameters, okay? And then that's the screen that we're going to see. So there are 6 parameters that we're going to refine on this screen, all at once, okay? So you check and refine, okay? Like once at a time, sorry, not all at once each time. So we're going to refine U first, then V, then W, then X, Y, and finally Z. So we're going to refine one by one of them. So you first check the U, and then you come in here, calculate, and then refine. We can see that the RW is going down. It was around 49 before refining that. Now it's around like 34, so it's a huge improvement. Okay. So let's focus, zooming in this area where the peaks are more present. Okay, so you can follow this way to see a better view. We can check the quality parameters in the covariance, accept the change. Then we can go to covariance to check the quality parameters. And you see that the RW that was around 49, now it's around 34. And the goodness of fit, which was around 11.8, now is around 8.22. So definitely is an improvement by refining the parameter U. Next, let's refine Z. So we come again to the same instrument parameters option here in the left side panel and check V. Okay, we can see how the things like the value for U changed in comparison to the initial one. So initially U was set to be 2.00, after refining, it became around like 3,539, okay? Now refine V, okay? Select V, then go calculate, refine. So yeah, so you can see that the visual improved a lot, mainly like this most intense peak that you can see here, that's around 19. Then these two peaks around 22 and 24, these other two around 27 and 29, okay? Definitely it's a big improvement, so let's accept the change. Then you go to the covariance to check the goodness of fit and the RW. So yeah, so the RW now it's around 20 and the goodness of fit around 4.8. Okay, so we can let's try to improve further. So that's all around like a good result, but I think we can still improve that. Refine the other profile parameters. So you come here, instrument parameters, and refine W. Okay, then you can calculate and refine. Okay, so it may have a slight improvement, so let's accept the new results. Then let's check the resulting covariance. So RW around 19.8 and going to fit around 4.77, so a slight improvement. Now let's start refining X, Y, and Z. Okay, so X, select that, then calculate, then refine. Accept, okay. So the covariance shows a RW around 18.4 and a goodness of fit around 4.44. So it improved slightly. Now let's go to refine Y. Check I and then click refine. Okay, so we see that like we have an improvement on this peak in the lower angle. So let's accept the result. And covariance, so 17.54 and goodness of fit around 4.22. Next, let's refine Z. So again, instrument parameters and check Z. And calculate. Then refine. Okay, so you come here, accept the result. And then you see the covariance. So slightly, almost nothing improved by doing that. Okay, so that's how we find the 6 parameters related with the profile function. The sample transparency. The sample transparency is one correction that can improve the agreement between the intensity of the experimental and calculated patterns. It considers the effects of X-ray absorption by the sample, although absorption can happen in lower extent than the diffraction. The transparency is described by the equation shown here in the slide. So minus 9000 over pi times r, where r is the diffractometer radius, times the absorption coefficient of the sample. Now let's refine the sample transparency. For doing that, in the left side panel, under the PWDR menu, we click in Sample Parameters, and then we select Sample Transparency. Okay, so next you see that 0, 0, we click Calculate and then Refine. Load the new result. And see in covariance what happened. So it's now it was around like I think 4.22, now 4.14, the goodness of it. Sample displacement. So another correction that will be refining throughout this refinement is the sample displacement. It can be understood as a physical shift of the sample from the diffractometer axis. And the sample displacement is described by the equation shown here, with pi times r, which again the diffractometer radius, times the sample displacement coefficient of the sample over 3600. Okay? So that's how the main equation that for sample displacement. So basically, when you do the refinement, that diffractometer radius is fixed, okay? It's given by the instrumental file that was input in the beginning of the refinement. So basically, when you check the sample displacement box, what you're going to refine is the sample displacement coefficient for the sample, so the SPD sample. That's what will be refined throughout this refinement. Then we refine the sample displacement. So sample parameters and select sample displacement. And then refine. So you accept this new result, and then you go in covariance. So we see that's a huge improvement. So that's around goodness of RW around 12.98 and goodness of fit around 13. So let's see the visual feedback here. So the peak positions, they all look really good, okay? So this peak around 11 matches well. This small one around 15 matches well. The highest intensity one around 19, that's huge match. This one around 23, 3.8, and this the other two around 28 and 28.5. So they all match really well. We have like few small peaks that the position is good, but like the width is could be better, but it's acceptable. So like this one around 13 and like this one around 21, okay? So I think that we can stop by here the refinement and consider acceptable and relatively really good. So the goodness of it around 3.13, okay? And you can see the difference pattern, how small the difference is, okay? So we can consider that acceptable. Saving and exporting the data. Now let's see how we can save this data, this refinement we did in such a way we should be able to use that in another softwares, in graphing softwares, okay? So we come here in the main screen and then you click export, okay? Then we export powder data as, okay? And then we select, so powder data as is the third option from top to bottom. And then on that, we select the option histogram CSV file, which is the fifth option from top to bottom, okay? And then we give a name to the file, okay? Final result, and save it. Okay, so it's saved in the folder we set that to be saved, okay? Then when you go there, to the folder where it was supposed to be saved. So we'll see that there will be like a CSV file, an Excel file here in the folder. And then we open that. And you see that the first rows is like the first 30 something rows are 2 columns, but they're all like the 34 row, it starts to be like a 6-column table, okay? So this table, the X is the tilt data position, the Y slash OBS is the observed, so the experimental pattern, the Y slash calc is the calculated pattern, and the Y slash BKG is the background, okay? We can set a difference pattern as well by setting up, like here on Excel, that's open here on my screen, a function that is the subtraction between the observed minus the calculated. That's going to give us the difference pattern as well. So we can go to any program you want, like Excel, Orange, and plot this data, and then have generated by us a plot similar to the one we see here in the screen, okay? So make them suitable to be have like a publishable quality figure. Thanks for watching. Do not forget to watch also the other videos of this experiment. Thank you so much. Bye.